Okay, hello everyone. My name is Brian and I am on the Why and How organizing team along with Ben and Alan. I want to welcome and thank everyone for attending our first Why and How of this season. We are very fortunate enough to have Hong-Hsi here to discuss diffusion MRI. Hong-Hsi has an MD and PhD and is an instructor at the Martinos Center, as well as the Department of Radiology at MGH. Since February of this year, he has joined Dr. Susie Huang's lab to study the brain microstructure using diffusion MRI. Hong-Hsi graduated from the National Taiwan University, where he obtained his MD, BS, and MS in physics. He obtained his PhD at the Center for Advanced Imaging, Innovation, and Research at NYU, and worked under the supervision of Dr. Dmitry Novikov and Els Fiermans. In his PhD, he focused on the diffusion experiments and numerical validations of biophysical models in the brain white matter, aiming at bridging the resolution gap between tissue microstructure and macroscopic MRI voxels. To extend the focus to the brain gray matter, he recently proposed imaging processing pipelines to increase the image resolution and signal to noise ratio and correct image artifacts. So clearly, he is very well qualified to discuss this with us. And if you ever have any questions throughout the talk, we have planned a time after the talk to answer them. So please leave them in the Q&A section. So without further ado, I will turn it over to Hong-Hsi.
Thank you for your introduction, Brian. So today I will talk about diffusion MRI. And here we show the stratigraphy result of the hippocampus. It looks pretty nice, right? So first question is, why do we use diffusion MRI? That's because in MRI, the voxel size or resolution is about 1 millimeter. But at clinical diffusion time, the diffusion length of water molecule is about 10 micron. It's consistent with the tissue microstructure. So diffusion MRI is a good way to probe the tissue microstructure in vivo. So the outline, first of all, we will introduce what is diffusion. So in 1827, people observed Brownian motion. It's a random motion of particles in the medium, like a liquid or gas. It describes the random fluctuations in the particle's position, and which means there's no preferential direction of flow. And after about like 80 years later, finally, Einstein gives the explanation of this phenomenon. So Einstein derived the Einstein Equation, where he defined the diffusion coefficient as the mean square displacement divided by diffusion time. And here, using this equation, we can define the length scale, which is diffusion length, which is root mean square of the diffusion displacement. And we can see the diffusion length is proportional to square root of time. So here shows some examples. In a cup of water, for example, at body temperature, its diffusion coefficient is about 3 micrometers square per second. And the tissue, like the brain white matter, there are myelinated axons. And because there are fewer restrictions along the axon, so its diffusivity is higher. Here shows that it's about 1.2. And for direction perpendicular to the axon, because there are more restrictions, there are cell membrane, myelin sheath, so the diffusion coefficient is lower, it's about 0.4. So the most simple diffusion is the free diffusion. So free diffusion is a diffusion in a free medium without restrictions. And we usually call it Gaussian diffusion because based on the central limit theorem, the diffusion displacement is distributed as a Gaussian random variable. So is PDF, probability density function, obeys the Gaussian distribution, and we can see its standard deviation of this displacement is given by the diffusion length. And in this case, in free diffusion, diffusion coefficient is constant over time. So in other words, the mean square displacement is proportional to time, as shown in the right figure. This green curve, this green line, it shows that the mean square displacement is linearly proportional to time for free diffusion. And the example includes the cerebrospinal fluid, CSF, in the human brain. At body temperature, the diffusivity of CSF is about 3 micrometer square per millisecond. And there's another commonly used unit, is millimeter square per second, and we can see there's additional 10 to the -3. And there are two other diffusion. There are hindered diffusion and restricted diffusion. So they are diffusion in the presence of tissue microstructure. And we usually call it non-Gaussian diffusion. And because the cell walls introduce correlations between random motions, so the central limit theorem does not apply. So in this case, the diffusion displacement, the PDF of diffusion displacement does not obey the Gaussian distribution. And here we said that the cell will introduce correlation between random motions because considering that when a water molecule collides, like hit on the membrane wall, and then it will bounce back. So its velocity is in opposite direction. And this opposite direction in velocity give us the correlation between the motions. So it is not completely random. In this case, diffusion coefficient decreases over time. And it is very important to know that diffusion coefficient cannot increase over time. It must decrease over time. If it increases over time, then there's another case called IVIM, intravoxel random motion, but that is not diffusion. So hindered diffusion in a hindered diffusion is a diffusion in a connected space. For example, in extracellular space, like these blue trajectories here. And the restricted diffusion is diffusion in closed space, for example, in the intracellular space. And if you look at their mean square displacement, we can see that for hindered diffusion, mean square displacement grows with time slower than for free diffusion. And for restricted diffusion, the mean square displacement will increase over time at the beginning and gradually approach to a plateau. And this plateau is given by the cell size because it cannot diffuse beyond the cell size. And there's another way to categorize diffusion, which is isotropic diffusion and anisotropic diffusion. So isotropic diffusion means that the diffusion coefficient is the same in all directions. So example is like CSF, which is free diffusion, or the diffusion inside a spherical in a cell of spherical shape, like a soma cell body. Another diffusion is anisotropic diffusion, which means diffusion coefficient is not always the same in all directions. The example includes the brain white matter, which has axons. So as we said, the diffusion along axon is more free, the diffusion coefficient is higher, and diffusion transfers to axon has lower diffusion coefficient in that direction. And then how do we usually measure diffusion with MRI? So MRI is handy, diffusion is dandy. So diffusion MRI is the sweet spot. So when we measure diffusion using MRI, we usually use pulse gradient spin-echo sequence, or PGSE. So the RF pulse is the commonly used spin-echo sequence with 90° for excitation and 180° for refocusing. And the G, and we add additional pair of diffusion gradients to get the sensitivity of the diffusion random motion. And the G is the gradient strength, and big delta is the time interval between pulses, and little delta is the pulse width. So it is basically the spin echo sequence with a pair of diffusion sensitization gradients. So when we apply diffusion gradients, we get the diffusion of phase, or water molecules get the diffusion of phase. And we notice that the diffusion of phase during the first and second pulse gradient has different sign because of this 180° refocusing pulse. And second, we notice that the diffusion of phase during each gradient pulse is proportional to the position of the water molecule. In other words, the diffusion phase is proportional to the diffusion displacement. So if we have a water molecule does not diffuse at all, in other words, it's a stationary spin, and there's no motion, there's no diffusion displacement, its diffusion phase is 0. So there's no signal decay. But if the water molecule diffuse and the diffusion displacement is not 0, then the diffusion phase is not 0, and this phase will introduce signal decay. So this is how we measure diffusion using MRI. So after some mathematical calculation, we can get this equation. The diffusion signal is the non-diffusion weighted signal S0 times exponential minus BD. So S0 is non-diffusion weighted signal, but we need to notice that it is T2 weighted. It is not diffusion weighted, but it is T2 weighted. And the B is the B value. We usually call it diffusion weighting, and the commonly used value is 1,000 over second, 1,000 second over millimeter square. And the B value is related to the grain strength, the pulse width, and the time interval between pulses. So we usually use this equation to calculate the apparent diffusion coefficient of ADC. So here shows that we can measure diffusion signal at different diffusion weighting or B value. And then we can fit the signal in a voxel using this. We can fit this equation to the signal in each voxel and get the estimate of apparent diffusion coefficient. But usually we only have 2 measurements. The first measurement is non-diffusion weighted signal. And second measurement is diffusion weighted signal at 1 B value. And then we will take the ratio, take the log, divided by B value, and give a negative sign, and this is the apparent diffusion coefficient. And we need to notice that diffusion coefficient has an isotropy. So in other words, when we apply diffusion gradients along the white matter axon, then we get the diffusion signal along this direction, and we'll get the diffusion coefficient along this direction. And if we apply diffusion gradient transfers to the axon, then we get the signal transferred to the axon, and also get the diffusion coefficient transferred to the axon. And because the diffusion coefficient is higher along the axon, in other words, the diffusion signal is lower when we apply gradients along the axon. So here shows some example. For example, in Kubricks Calcium, this direction is left-right. So when we apply the diffusion gradients in left-right direction or X direction, you can see the diffusion signal is pretty low in this fiber tract. And it is the same for optic radiation in anterior posterior direction. It's the same for the corticospinal tract in the inferior superior direction. And we can see when we apply gradient direction in X direction, left-right direction, the ADC in Kubricks Calcium is pretty high because the fiber is in left-right direction. And it's also the same for other fiber tracts. So the diffusion signal and ADC seems to have a reciprocal relation. But higher device signal corresponds to lower ADC, and lower device signal corresponds to higher ADC. And clinically, we usually look at we don't want to see this like directional anisotropy. So we usually combine the information of all directions and define a trace diffusion weighted image and ADC map. So trace image is obtained by combining diffusion weighted images in all directions. So we usually take the geometric mean, and we can see that the trace image is not only diffusion weighted, it's also T2 weighted because of this S0 is T2 weighted because we measure it using spinnaker. And the ADC map is a directionally dependent diffusion coefficient combined into a single value. We usually just take the direct mean. And we can see the contrast in ADC map is very flat in the brain. And for the reference, the ADC in CSF is about 3 micrometers squared per millisecond. And the brain tissue, not only in white matter, but also in gray matter, the diffusion coefficient is about 1 micrometer square per millisecond. And then there's the commonly used model is called diffusion tensor imaging, or DTI. So why do we use diffusion tensor imaging? Because we want to describe the anisotropic diffusion by limited amount of variables. So because the diffusion coefficient is different in many directions in 3D, and there are infinite number of directions in 3D. So, but we only want to use a few variables to describe its anisotropy. So that's why we use diffusion tensor imaging. And here we show that the diffusion tensor is a symmetric tensor symmetric matrix. So there are only 6 independent variables, and we can use eigenvalue decomposition to decompose into this diagonal matrix with its eigenvectors epsilon 1, 2, 3. So its eigenvalue lambda 1, 2, 3 defines the diffusion coefficient along the principal directions, and epsilon 1, 2, 3 are its main directions of this tensor, and the epsilon 1 we usually call it principal direction, which roughly decides the axon direction in the white matter voxel if there's only one fiber. So diffusion tensor provides an optimal frame of reference based on the diffusion ellipsoid, whose principal direction, epsilon 1, usually parallel to the fiber direction in white matter. And to fit the DTI to the data, we need to acquire at least one non-diffusion weighted image for S0 and DWIs of 1B shell in 6 different directions. Why 6 different directions? Because there are 6 independent variables in diffusion tensor. And the size of diffusion ellipsoid defines the mean diffusivity equivalent to the ADC map, and the axial and radial diffusivity can be obtained by lambda 1 and lambda 2 and 3. And also the shape of diffusion ellipsoid defines the fractional anisotropy, ranging from 0 for isotropic to 1 for extremely anisotropic. This is one of the most used measure. And we can see this here shows an example FA map. And you probably also see this diffusion encoded color map, or DEC map, which is actually the color FA map. Its intensity is given by FA, but its color is given by the principal diffusion direction. And there are many studies implies FA as a white matter integrity, but it is far from definite. And FA can be easily affected by the SNR and the resolution, because when the voxel is larger, there are more fibers in many directions, so FA will be lower. And when there is noise, the noise will bias the diffusion tensor estimates, and noise will make the FA higher. So low SNR leads to higher FA, and low resolution leads to lower FA. I know people usually have a hard time to memorize this color encoding. So just imagine that when we drive, we hope that there's also always green light so we can drive ahead. So anterior posterior direction is green. In other words, for people driving in another direction, left-right direction, they see the red light. So left-right is red. And we want to have a good weather, so we want to see the blue sky, so up-down direction is blue. And we can also use diffusion tensor to do chromatography. So the estimates of white matter connectivity patterns in the brain from white matter chromatography may be obtained using the diffusion anisotropy and the principal diffusion directions. So here shows the chromatography in the SCP gallery, and this is the chromatography in the hippocampus. Okay, so this is probably the most important part of in this talk is about the practical considerations in position. So in our diffusion MRI measurements, diffusion sensitization gradients induce a random spatially varying phase over the object before the echo readout, leading to ghosting and signal voids in images of multi-shots. So here shows here shows the phase map given by the navigator in each shot. If we do the multi-shot, shot by shot diffusion measurement instead of using EPI. And we can see the navigator shows that if we turn on the diffusion gradients, and diffusion gradients will induce a random shot-to-shot phase variation. And there's no way we can combine all the shots to create a reasonable MRI image. There must be signal voids and ghosting. So to overcome this problem, the solution is to do diffusion measurements using single-shot echo-planar imaging. The pros is it avoids the most ghosting and it's very fast. The cons is it has low SNR, low resolution, and a lot of image artifacts. So the figure in the middle shows echo-planar imaging. So basically, we acquire all case-based lines in one shot instead of one line a shot. We acquire all lines in single one shot. So it's pretty fast. But we can imagine that because let's recap. So for direction parallel to each line's frequency encoding direction, for direction perpendicular to all lines is phase encoding direction. Then we can imagine that when we acquire each shot in when we acquire each line in frequency encoding direction in forward domain, the time is pretty short. So any kinds of phase error accumulated in one line in frequency encoding direction is small. But if we look at the case-based data in one line in the phase encoding direction, the sampling time along phase encoding direction is very, very long because it goes through all shots. So any kinds of phase error accumulated along the phase encoding direction will be huge. So almost all the image artifacts of EPI is along phase encoding direction. Okay, so the first thing is low SNR and low spatial resolution. So to accommodate diffusion gradients and long echo trains, the echo time is pretty long, as shown by this like red arrows. And the d-divided is T2-weighted because it is measured by spinnacle. So it decays so it has an exponential decay with a decay time constant T2. So it leads to a low signal to noise ratio because echo time is too long. So first solution is to shorten echo trains by using parallel imaging or partial Fourier or other fast imaging techniques. And the second solution is to shorten the diffusion gradients by using strong gradient and high through rate. So this is why we work on the human connectome project with very strong diffusion gradient system. Okay, so secondly, the SNR. The SNR is proportional to the voxel size, and higher resolution or smaller voxel size leads to lower SNR. So EPI has low SNR. So the first solution is to average over many repeats. So in a body imaging for prostate, when we want to acquire a d-divided, we usually average over more than 40 d-divides to get a clinically acceptable d-divided. And the second solution is the denoising in our post-processing. For example, using matrix d-divided denoise function, and we'll introduce it later. Then the second artifact is the Necroscopes or Energy-to-Ghost. So Necroscopes can originate from many sources that lead to signal amplitude modulation, phase inconsistency, or displacement of case-based data. And these errors typically alternate between even and odd echoes. The common cause include eddy current, concomitant magnetic field, and gradient group delay. So if you look at this EPI echo train, you can see that some lines are acquired from left to right, like blue lines, and some lines like red lines are acquired from right to left. And usually they have a mismatch between these odd lines and even lines in K-space. It can either have a constant phase difference or they can shift it in K-space. So here shows that the data, the original data without correction, we can see the zigzag pattern in this central case echo. So which means the outlines, even lines, they actually have a shift in K-space. And the common way to do the correction is to do a reference scan. And actually almost all the clinical sequence or WIP sequence has this kind of reference scan correction. And the third artifact is distortion due to B0 field inhomogeneity. So B0 field inhomogeneities and concomitant fields result in image distortion, and they affect the lights independently of the different gradients and do not produce misregistration in different lights. In other words, if the phase including direction is the same, if the echo spacing is the same, then all the DWIs has the same distortion because of the B0 field homogeneity. There's no misregistration. They all have the same distortion because of B0 field homogeneity. And distortion are more evident when phase including direction is oriented left-right, since the natural left-to-right symmetry of the brain is disrupted. So we can see because the brain is in the left-right symmetry. So if we apply the phase including direction in left-right direction, the brain really looks very distorted. But if we apply the phase including direction, anterior-posterior direction or PA direction, posterior to anterior direction, the brain still looks symmetry, so it doesn't look that weird. So anterior-posterior direction is the customary orientation for phase including direction in most EPI. To correct this distortion, we can either acquire a B0 field map or acquire flip up and flip down images. And then we can use FSL top up to correct this artifact. So what does the flip down means? It means that we can acquire the DWI. We can acquire B0 image, a non-diffusion weighted image in the left-right direction and also right-left direction. And then we can use these two images to estimate the B0 field map and correct the image. And another common way is AP and PA view. Okay, so there's another distortion because of eddy currents. So when gradients are rapidly switched on and off, the eddy currents are induced in conducting parts of the magnet. Eddy currents produce distortions that affect each light differently and result in misregistration of different lights. So, and the commonly used toolbox is FSL eddy to correct this eddy current distortion. And we can see it can lead to the eddy current distortion can lead to a translation and the shearing and maybe the size scaling along the phase including direction. Okay, maybe a faint along the phase including direction. So here shows an example. So the left figure shows like a happy brain jumping like left and right. That's not because the subject is happy. This is because of the eddy current. And after correction, we can see this brain looks like a standstill. So contrast change over different gradient direction. And the last artifact I would like to introduce is fat-water shift. So fat and water differ in resonance frequency by 3.5 ppm, which is equivalent to 220 and 440 Hz at 1.5 and 3 Tesla. So for conventional imaging, like shot by shot, multi-shot, shot by shot, one shot per line, this chemical shift occurs in the frequency including direction. But in EPI, however, the chemical shift occurs along the phase including direction due to the very long echo train. Because of the same reason, phase error mainly accumulates along phase including direction. And the solution is to do the fat saturation. So on the scanner, you can see there are some options. For example, fat sat weak, never use it, it doesn't work. Now there's fat sat strong. You can use it, it works fine. But I strongly recommend to use spare, use adiabatic pulse and inversion recovery to saturate the fat signal. And it is the best, but it will increase your TR, your repetition time, so it's kind of slow. But for research, I highly recommend to use spare. And you can see in EPI, because it's on long echo train, the fat water shift can be like 30%, 40% of a field of view. So you have to do the fat saturation. If not, if you don't do it, then the fat signal will contaminate into the brain. Okay, then there's another thing is the choice of p-value and directions. So for reliable estimation of ADC, the optimal p-value is about B times D around 1. For example, in white matter, if diffusivity is 1 micrometer squared per millisecond, the optimal B value is about 1 millisecond over micrometer squared. And if we change the units a little bit, we'll see that it's 1,000 second over millimeter squared. That's why most of the clinical sequence in the human brain use a B value of around about 1,000 second over millimeter squared. And the gradient directions in each B shell should be isotropically distributed over a sphere or a hemisphere. So you can see in the left figure, it shows the FA map obtained from 2 different protocols. The first protocol has anisotropic gradient directions, and the second protocol has isotropic gradient directions. And we can see it's very important to have isotropic gradient directions distributed over a sphere or hemisphere. And the spherical sampling with high angular resolution distributed optimally across shells is the most common approach now. And multi-shell acquisitions have greater sensitivity to fiber crossing than single shell schemes. So we can see in the fiber crossing region, single shells can show like relatively fewer directions in fiber crossing region, but multi-shell data can show more fiber directions in fiber crossing region. And then there's also important part of its talk is the image parsing pipeline. So goal of image parsing pipeline is to amend the lowest SNR and artifacts in diffusion MRI and restore its quality and integrity while preserving spatial resolution. So as we know, most of our artifact can go away if we apply Gaussian smoothing over space, like Gaussian filter over space, and like this ringing or noisy stuff just go away. But we still want to maintain the spatial resolution, so we don't do that. And there are some pipelines, and here we usually use diffusion HCP processing, or some people call it free surfer. It's developed by FinRip, and it includes gradient nonlinearity, Physio, Emogenetic distortion correction, eddy current, and motion correction. And the second pipeline is Designer. It's called Designer. It's developed by at NYU. It includes denoising, Gibbs ring correction, rational noise flow correction, and also distortion correction and the motion correction. And the third pipeline here is the QSI prep. It's recently published in Nature Methods, but I won't introduce it because it is very similar to Designer. So first thing is gradient nonlinearity. So with the oblique slices relative to the scanner's coordinate systems, it is required to correct the image distortion due to gradient nonlinearity of magnetic field generated by each gradient coil. And the correction is required for SCP SCARA scanner, but it may not be needed for standard scanners. And the correction requires a text file from the vendor with a spherical harmonics expansion representing the gradient nonlinearity of each gradient coil. So you need to get the file from the vendor. It's usually on the scanner. And the toolbox here is the free surfer. It has a function, meta function called gradient nonline on warp. And we can look at these. So on our clusters, basically we have this function, and you can look at this go to the free surfer web page to get more information. And when you do the acquisition, if you don't want to have so much gradient nonlinearity, if distortion, you can actually don't rotate the field of view at all, and keep the brain at the isocenter of the scanner. Then the effect of gradient nonlinearity will be smaller. And then we'll introduce Designer pipeline. The full name of Designer is Diffusion Parameter Estimation with Gibbs and Noise Removal. So the first thing is denoising, the second is Gibbs ring correction, the third Rational bias correction, the fourth is Physio Emogenetic distortion correction, the fifth is eddy current plus motion correction, and sixth is B1 bias field correction. But I feel that for like 3 Tesla and lower field scanner is B1 bias field correction is kind of optional. So the first thing is denoising. So each dBi has different signal contrast because the beta is different, gradient direction is different. but they all have the noise in all the devices has the same statistics. So typically, diffusion MRI data exhibits sufficient redundancy due to oversampling in B-value and gradient direction, or we usually call it Q-space. And redundancy in data is commonly pursued by a local and non-local patch for spatially varying noise. So for example, we have B0 image and multiple DWIs. Here we show like M brain volumes in total. Then for one specific voxel, we can get a 3D, 2D, or 3D patch around the voxel in B0 image and all the device. And then we can perform the single value decomposition, or we can use PCA, this principal component analysis. And then in PCA domain, the thermal noise only eigenvalues obey the universal matching capacitor law. So when we apply SVD or PCA, the eigenvalues, actually we plot this histogram, the noise components will show this beautiful matching capacitor distribution. It represents the Gaussian noise. So Gaussian noise in image space has infinitely long tails, but in the PCA domain, it's a closed distribution. So if we identify the minimal and maximal value of this distribution, we can identify the noise component, we can calculate the noise level, and if we remove it in PCA domain, we do denoising. So an objective threshold on the eigenvalues for PCA denoising can be derived from the noise level. And empirically, we need the B0 image plus device, like the number needs to be more than 30. We need more than 30 images. So here shows the results. So the toolbox, commonly used toolbox is MR tricks divide the noise function. And here shows the commonly used command line for denoising. It's very simple. You just need to have one input, and you can use their default setting, and it will give you the denoise image and the noise map. So left figure shows the image before denoising, right figure shows the image after denoising. Then we can see the noise just mostly gone. And then is the Gibbs ring correction. So Gibbs ring is an artifact manifested as spurious oscillations in the vicinity of sharp image gradients at tissue boundaries, like the boundaries between CSF and gray white matter. And the origin is the truncation of K space during MR acquisition due to limited scan time. So we can only scan the K space data within the range, within the K max. So this truncation at the K max leads to this ring artifact. As the image is reconstructed on the discretized grid, the severity of the ring artifacts depends on how this grid is located with respect to the edge and oscillation pattern of this function. And the ring artifact can be corrected by reinterpolating the image based on local subvoxel shifts to sample the ring pattern at the zero crossing of the oscillating sync function. So for example, the black line shows the edge in the image, like the tissue boundary, and the red shows the actual image intensity with ring artifact. And usually our discretized image, a sample at this like valleys and peak of this ring pattern. But if we can locally find an optimal shift and shift the image locally in a displacement smaller than the voxel size, then we can find an optimal shift, sample the signal intensity at this zero crossing position to minimize this ring artifacts. So this is a very smart way to remove this ring artifact. So the toolbox is implementing MR tricks in MR Gibbs, and the input is also very simple. We can just use its default setting, and you have the input, and you get the output. It's very fast. So this is the before correction, this is after correction. We can see before correction, there are a lot of rings in Kubricks Calcium around the ventricle. After correction, most of the ring artifacts gone. And the last one is Rayson bias correction. So noise in magnitude device is governed by a Rayson or non-central chi distribution that creates a positive noise floor bias in images of low SNR smaller than 2. So the MPPCA denoising can only remove the noise fluctuations, but not the noise floor. So fortunately, the noise floor can be estimated by using MPPCA denoising. So the solution 1 is to eliminate the shot-to-shot phase variation in each complex value delay and either denoise an average over real value delay, but it's kind of optional. And the second solution is the expected value of true signal intensity can be estimated by the measures magnitude signal and the noise floor when SNR is higher than 2. So we can just use this approximate equation to correct the Gaussian noise floor. So N is the measurements and sigma is the noise map given by MPPCA denoising. And then we get eta, which is the corrected image intensity. So there's no specific toolbox. This equation is too simple. And here we use MRCOC function as an example. So it's just one command line to do this job. It's very simple. So we can see the results here. Here shows a spherical mean signal of magnitude image and real value image with MPPCA and Russian noise floor correction. And we can see for high B value higher than 5,000 and up to 30K second over millimeter square, we can see the effect of this expression on bias correction. Okay, then there are Physio Emogenetic distortion correction. Where we introduce is a region. So the full solution is to acquire P0 field map and blip up, blip down images, and then we can correct the distortion completely. But it took a lot of time. So people usually either only acquire P0 field map or measure blip up and blip down images and use the toolbox, FSO top-up toolbox. And when we use FSO topbox, we need an additional non-diffusion weighted image in reverse spacing and polarity, for example, AP plus PA or LR plus RL. And here it shows the command line. So we can see before correction, the AP and PA views have different distortion. After correction, and correct it pretty well. And the next one is eddy current plus motion correction. Again, the toolbox is FSL eddy. It is beneficial if the data is acquired with either a set of diffusion encoding direction that span the entire phase sphere and not just a half sphere, or you can acquire a blip up, blip down phase encode reverse acquisition, or with both, because usually we combine the usage of eddy with top up. And if the data has neither been acquired on a whole sphere or with reverse phase encoding direction, there's a good chance that it will still work well. So just try it. It may work. And eddies attempts to combine the correction for susceptibility and eddy currents movements so that there's only one single resampling. That means we need to inform eddy of the results of top-up. So we usually use top-up first and input the information from top-up into eddy and use them together. And eddy works for single multi-show different diffusion data, which means that it doesn't work for DSI data. But maybe you can try and it may work as well. So when we use FSO eddy, we apply top-up first. It's optional. It's not required actually. And then we need to create brain mass. We need to create some other files to inform the phase encoding polarity and total readout time. And this the command line is a bit long, but it's still fine. And here shows the result as previous slides. And then I will spend just a little bit of time talk about microstructure imaging and advances in diffusion MRI acquisition. So modeling is to select the most relevant features. And features means the degrees of freedom. So the left picture is the ground truth, and the single picture is just the interpolation. We can say it's a signal representation with the basis of the pixel. And the right figure is actually a tissue model, which has assumption. And here the assumption is this is a human. So it has specific features like eyes, nose, mouth, ears, or presence. So actually, this is the essence of microstructure imaging. So when we into this field, we usually feel that, oh, there are so many models. We're very excited. At the end of the day, we just go back to use the signal representation of DTI and DKI. Yeah, so later I will introduce DKI too. So there are two different kinds of models. The first one is signal model or signal representation, which is DTI or DKI, which use some basis to describe a signal. And there's another way to represent a signal is called mean apparent propagator MRI. And another group is tissue models. For example, for white matter, we have WMTI and Noddy. I will introduce them later. And gray matter, we have Sandy to include the soma compartment. And we can also include the exchange between neurite and extracellular space. And there's also axonal diameter mapping, like active X, at caliber, auto scaling at high p value. There are a lot of models. It's like a zoo of models. Okay, so let's introduce the diffusional kurtosis imaging. So for Gaussian diffusion in homogeneous liquids, the diffusion signal decays as expansion minus BD. However, in biological tissues, diffusion is usually non-Gaussian. And the deviation from the Gaussianity can be described by a natural extension of DTI. So here we can see there's additional term with a variable called K. So K is the kurtosis. And due to the symmetry of diffusion tensor and kurtosis tensor, diffusion tensor has 6 independent variables, as we introduced, and kurtosis tensor has 15 independent variables. So in other words, if we want to do a DKI, we need to obtain at least 2 B shell data. We usually use like 1,000, 2,000. And the lower B shell needs to be acquired in more than 6 independent directions, and higher B shells in more than 15 independent directions. And we can see diffusion signal is a monotonically decreasing function. In the brain, diffusivity is 1, kurtosis is 1, implying the upper bound of B value is 3,000 second over millimeter square. So that's why when we apply DKI measurements, we perform DKI measurements in the brain, we usually use like B 1,000, 2,000, or 3,000 is borderline already. And we can see because it's actually a parabola function for the log signal. So we need to use B value lower than 3,000. And the kurtosis manifests the tissue inhomogeneity or complexity within the voxel. So if there are diffusivity differences of tissues within the voxel or cell size distribution, orientation dispersion, or partial volume effect, any kinds of tissue inhomogeneity will lead to higher kurtosis. And then we can also define axial kurtosis, real kurtosis, mean kurtosis based on principal direction of diffusion tensor. Another application is called white matter track integrity, or WMTI. So WMTI relates DKI metrics directly to white matter microstructure. So at long time, the intra and extra-axonal space can be modeled as Gaussian compartments. So we usually assume that the diffusion along the intra-axonal space is Gaussian, and transverse, this diffusivity is almost 0 because the axon is too thin, too narrow. And for extracellular space, the diffusion is Gaussian, but it's anisotropic Gaussian. And then we use some metrics from DKI. We use maximal kurtosis over all possible directions, apparent diffusivity and apparent kurtosis in gradient direction G hat. And then we can estimate intra-axonal water fraction, extra-axonal diffusivity, intra-axonal diffusivity, apparent axial diffusivity of intra-axonal space, apparent dispersion, apparent axial and radial diffusivity of extra-axonal space, and their ratio called tortuosity. And here shows some typical maps in white matter of WMTI. And the last model I will introduce is neurite orientation dispersion and density imaging. It's called Noddy. Actually, a lot of people are using it. So the tissue is separated into 3 compartments, include intra-axonal space, extra-axonal space, and CSF. And the intra-axonal space is composed of orientationally dispersed sticks based on an axially symmetric Watson distribution. And extra-axonal space is an anisotropic Gaussian compartment with the same distribution. with the same orientation distribution. And CSF is an isotropic Gaussian compartment. And because there are so many variables in this model, so we need to apply some constraints. For example, the diffusion, the axial diffusion, the axial diffusivity for intra and extra axonal space are about 1.7. The diffusivity in CSF is 3, and we need to relate the diffusivity of extracellular space in along and transverse to axons. And so, in other words, there are only 3 independent variables in this model, including the neurite density index, actually intra-axonal volume fraction, and isotropic volume fraction, the volume fraction of the CSF, and orientation dispersion index, or ODI. And this is the typical maps of these metrics. And for the acquisition of Noddy data, we need to acquire at least 2 B shells because there are 2 unknown for the volume fractions. And sometimes we assume that the volume fraction of CSF is 0, for example, for white matter away from the CSF. In this case, acquisition only requires 1 B shell, and Noddy actually degenerates and is no more than the DTI. This is very important, but very few people notice that. Okay, so last part is advances the diffusion MRI acquisition, but I think we are running out of time, so I will stop here.
Thank you so much for that. So I have a few questions to ask. So I'll start with some that hopefully will have an easier answer. So one asks, and this is about one of your earlier slides, why is there a factor of 2 pi in the gamma factor in the B-value formula? So it's one of your much earlier slides.
Two pi. What's the 2 pi mean? Why is there a factor of 2 pi in the gamma factor in the B-value formula? That is because sometimes we see there's like a 4 pi square in the formula B-value because people use gamma bar, and gamma bar is gamma divided by 2 pi. So when we use gamma, the unit we use is megahertz, right? Megahertz per Tesla. But when we use hertz instead of other units, there's no 2 pi there. So when we represent gamma using megahertz over Tesla, we are talking about gamma bar, which is gamma over 2 pi. In that case, we need to multiply 2 pi back into B value. That's just about the definition of unit of gamma.
Cool, thank you for that. Oh, so did you see the clarification? I don't know if you are looking at the comments. It says, in other words, is the gamma, okay.
Yeah.
So I believe you answered that. So there's another question that, it's about the imaging processing pipelines you discussed. Are these processing pipelines designed specifically for brain imaging, or can they be used for more general purposes, say for body imaging?
In general, it could apply to body imaging for denoising, for greater nonlinearity, denoising, the Gibbs ringing, spatial noise for correction. But for FSL top up and eddy, in other words, distortion correction due to Physio inhomogeneity and eddy current and motion, they are specifically designed for brain image. So if you want to do image processing in a body imaging, we usually use elastics. There's a co-registration tool called elastics. It's a little bit hard to use because it has so many inputs and you have to explore the optimal input. But for body imaging, we don't have a lot of choice.
Very cool. And so my question was kind of about what I assumed you would have discussed in the advancement section. So I work in a vision lab, and so we are looking at very fine structures like thin and thick type columns. And so we were kind of discussing and interested in your current work on increases in gray matter resolution. So I don't know if you want to briefly talk about that, since you didn't even really get to introduce it.
Yeah, so you mean like a high resolution image in the gray matter?
Yeah, so because obviously diffusion imaging really excels in white matter, but when it comes to
Right.
fine structures in gray matter, it
Right.
usually struggles.
Right. So I remember like 3-4 years, people still saying that, oh, we shouldn't do diffusion measurements for gray matter. But now everyone's doing diffusion measurements in gray matter. So yeah, indeed, for diffusion measurements in gray matter, the problem is the resolution, because the cortex is very thin. And the second problem is SNR, because when we have high resolution image, voxel size is small, so SNR is low. Or for example, if we focus on deep gray matter, the SNR is usually low at the brain center. So for example, for the resolution, there are several ways to increase high resolution image. For example, we can use G slider. So in G slider, we basically has a very special slice excitation. And we use different combination of slice excitation to increase the resolution across the slice, but still maintain the SNR, because we still acquire a slab image. But for each slab image, they have different slice excitation. So different slice profile. And we can use this independent slice profile to increase the kind of super resolution, increase the resolution across the slice, but still maintain the SNR, because we get a slab image. So there are more spins in a thicker slab. And another way is to do post-processing. So for the post-processing, so first thing we can do denoising, of course. And so far we apply denoising on colloidal combined image, but actually we can do denoising in complex data in colloidal level. So we can have more data redundancy to denoise, because we said we need more than 30 images to do denoising. But if we have like 60 coils, 64 channel head coil, we have 40 coils images, 60 coil images, for example, we have more data redundancy to denoise the image. So we can further bring down the rational noise floor at the same time. Another way is to do the super resolution. So 2 years ago, we used MP-RAGE, which has the high resolution details in T1 weight image. And we have a low resolution DWI, which has the distortion all corrected. And then we can do curstration, and we can use a very simple self-similarity, which use a Gaussian, just use a simple Gaussian kernel to do a smarter interpolation. So when we do the interpolation, there are two ways to decide the weights. The first way is to use the distance. So that's why we usually do the linear interpolation, the cubic interpolation. The second way is to decide the weights based on the signal differences. So when we look at the two voxels, we can look at their signal differences in T1 weighted image and signal differences in diffusion weighted image. And then we can use these weights to do a smarter interpolation to increase the resolution of diffusion weighted image. It's called self-similarity. Actually, this is a very conservative, very conventional way to do the interpolation, and it works pretty well. So actually the hippocampus stratigraphy I showed in this slide, actually I use this super resolution method in HCP data. So the resolution is about 0.7 millimeter isotropic. So we actually can achieve sub-millimeter resolution just by doing post-processing. And it's hippocampus, it's not cortex, so deep gray matter works too. And we can see these red chunks, like red fibers, they are obvious. They are fibers going posteriorly and going up and going out from the fornix. And we can see in high resolution, we can see these red fibers are groups into several clusters. And there are some hypothesis saying that it may have some it may form some functional units, but it's still a hypothesis. But indeed, we observe these groups in anatomy.
Wow, that is really cool, and clearly there's a lot of progress in that specific aspect. So it seems like that is all the time we have right now for questions. So if anyone has more questions, please reach out to Hong-Hsi. And again, we'd like to thank everyone for attending, and then especially, obviously, Hong-Hsi for that very informative presentation. So thank you so much for joining us, and look to see you guys next time. Thank you, Hong-Hsi.
Thank you. Bye-bye.